had one lecture from Colin, which was about doing inversions of radiative transfer techniques, where you had a spectrum and you matched it to this semi-analytical model that had been cooked up. Let's see, why don't I turn this on? Yeah. Whoops. Okay. So there we have this mathematical model. It's got some free parameters. You basically find the best fit of the model to the spectrum, and that determines the values of these parameters, which can be chlorophyll concentrations or whatever it is you're interested in. So that's a general sort of spectrum matching technique. What I'm going to show you today is, rather than taking your RRS spectrum and matching it to a model, you match it to a database of pre-computed RRS spectra, and we'll see how that works. And you can get some things out of that that you can't get very easily out of the semi-analytical techniques like Colin talked about. So I'm going to demonstrate this with retrievals of bottom depth and bottom type in optically shallow water. And optically shallow simply means that reflectance off the bottom is making some significant contribution to the water leaving radiance. And of course, you know, water could be optically deep if it's a meter deep, if it's really, really scuzzy water, and it could be optically shallow if it's 30 meters deep, if it's clear water. Okay, so first of all, who cares about shallow water? Well, the military, of course, wants to get maps of bathymetry and bottom classification, and bottom classification means things like, is it sand, is it coral, is it mud, you know, is it hard, is it soft, in what they call denied access areas, which is places where they're not allowed to go, and they want this in case they want to invade this country. Not that that would ever happen, but anyway, so, and they also want maps of how clear the water is, so when they put divers in the water, they know how far they're going to be able to see and when they look for things. So they're interested. Ecosystem managers want to map and monitor bottom type and water quality for things like managing coral reefs and seagrass beds. Those are both really big things in the U.S. So places like the state of Florida or the state of California that have big recreational investments and big fisheries investments in, like, how healthy are my coral reefs, how are my seagrass beds doing, how are my kelp forests doing. They want to be able to, like, fly over some way, generate a map of bottom type and bottom classification, or if a hurricane comes through, you want to be able to fly over and see what changed. And of course then so those are episodic events, meaning they just occur now and then, or, you know, oil spills, that kind of thing. But also just long-term monitoring to see what things like climate change or runoff of fertilizers from adjacent farmland, you know, what's that doing to the water, what's it doing to the seagrass beds, and so on. And you need these maps at scales of like a meter per pixel, or maybe at the coarsest, maybe 10 meter size pixels. So even if you have the satellites that do everything you want, they're maybe going to give you a kilometer size pixel, and that's not going to show much about a coral reef. So you want high spatial scale, and sometimes you maybe want to get this thing all done within a day. Yeah, Colin.
They also, a lot of managers and programs are really interested in this high mapping so that they can want, in addition to regular storm runoff, how that responds to sea level rise. And so they're really interested in mapping your shoreline imagery so that they can look at how waters enter from storms.
Yeah. One of the hot topics in our field today is the land-ocean interface, where you've got, well, you know, an estuary like the Damariscotta, but also like around the Gulf of Mexico, you've got all of these salt marshes, and they're very important for like catching pollutants off the land before it gets into the ocean. They're important for decreasing the effects of big storm waves from hurricanes, etc. So the understanding things like the exchange of matter between like estuaries and marshes and the coastal ocean, those are really big topics. And you know, once again, you need to sort of like 1 or 10 meter scale imagery there. Okay, so we've seen in previous lectures that you can have statistical algorithms like, band ratio algorithms. Generally, these are applied today to multispectral measurements where you've got half a dozen bands in the visible, something like MODIS or VIIRS. And those algorithms work pretty well in the open ocean. We saw an example somewhere along the way where Heidi Dearson had this band ratio algorithm for retrieving bottom depth, and it works fine till the depth gets too deep, and then it starts becoming non-unique. So these kind of statistical or empirical algorithms, even though they can work very well sometimes, they often fail in coastal waters. And then there's a whole other problem here, which is when you're in shallow water, is how do you do atmospheric correction? Because you often can see the bottom, especially if the water's this deep. You'll be seeing the bottom out there at the band or the instrument satellite bandwidths where they're assuming water leaving radiance is 0 in order to do the atmospheric correction. So you have to find some other way to do atmospheric correction. And then a lot of now, especially airborne sensors, but then things coming down the road like PACE will be hyperspectral. So we have maybe 100 wavelengths or so and somewhere around 5 nanometer bandwidth. And these are the things that tend to get used in coastal and shallow waters. Okay, so yeah, we know what remote sensing reflectance is now. And what we're going to do is first create a database of remote sensing reflectance spectra. And for each of those spectra, we can use hydrolite, for example. For each of those spectra, we know what the water absorbing and scattering properties are. We know what the bottom depth was. We know what the bottom reflectance is. And so I got involved in this business, 15 or 20 years ago. And so I have a special version of Ecolite where I just read in huge data files of like AC9 data, bottom reflectance data, lists of bottom depths, and it just cycles through all combinations of everything and creates a big database of RRS spectra with each one of those flagged by what created the spectrum. So here's an example. So this is for a study in the Bahamas back in the 2000 era. So here's a whole bunch of absorption spectra, and these are sort of based on AC9 data from that area, but then I expanded that to have bigger and smaller values to make sure that somewhere in that set of absorption spectra, when I go to the Bahamas, there's whatever's in the water that day will some way be described pretty well by one of those spectra. And same thing for the total scattering coefficients, again based on AC9 data, and backscatter coefficients when there was a little bit of hydroscat 6 data and that sort of thing. And so I could take a couple of spectra there and then just kind of expand on it to greater and smaller values. So I have IOPs going in. I have databases I had 123 different measurements of bottom reflectance spectra in this Bahamas area. And that's everything from very bright sand to really dark, red algae and, so forth. So somewhere in this database of bottom spectra, for any place I look around the Bahamas, there should be a bottom that's fairly close to one of these spectra. So somewhere in there, I can describe the bottom. So I took all of those guys, then I ran this code at depths from a centimeter, quarter of a meter, on down to 30 meters, 50 meters, and in infinitely deep water. So all the IOPs times all the bottom reflectances times all the bottom depths, and that gives me something like 250,000 different possible remote sensing reflectance spectra, which created from Ecolite. I ran from 400 to 750 by 5 nanometers, and that was about a week of computer time of Ecolite just cranking out answers at like 1 a second there. Okay, so now I have this database. And here's just representative. Here's 1% of my 250,000 RRS spectra. So the idea now is you give me an RRS spectrum from the Bahamas, somewhere in there will be a spectrum that's probably pretty close to whatever you measured. Okay, so now to apply that, here's an airborne image of an area near Lee Stocking Island. This is Lee Stocking Island here. There's a couple of other little islands here, and then here's this water area, and you can see there's looks like that must be a bright sand bottom, and maybe that's Jeep, or maybe it's shallow, but it's got a dark bottom of seagrass, I don't know. And then there's some areas here that look kind of mixed. So anyway, what you do then is you pull out 1 pixel of your image, and you say, okay, so here it is. Then you search the whole database to find the spectrum in the database that matches this spectrum the closest. And there's a dozen different ways you can decide how close something is, and what works just as well as anything is just these squares difference, wavelength by wavelength. Okay, so then you find a spectrum. Here's the green spectrum here, and here's a red spectrum that almost lies on top of the green spectrum. So you say, okay, I found the closest matching spectrum here in my database that matches what I observed. And then you look in your little database and it says, oh, well, that's spectrum number 87,085, which was IOP set number 17, bottom reflectance number 34, and bottom depth was 2.75 meters. Well, then you go back to the database and say, what was IOP set number 17? Well, here it is. There's absorption, including water, scattering, and then backscatters times 50, so you can see it. And what was bottom reflectance number 34, that was a mixture of 80% sand and 20% seagrass, and the depth was 2.75 meters. So now I say, at this point right here, these are the IOPs. The bottom depth was a mixture of sand and a little bit of seagrass thrown in, and 2 3/4 meters deep. So that's how I do my retrieval. And then you go to the next pixel, pull out the spectrum, match it, and away you go. So pixel by pixel. And I'm assuming here that we've already done the atmospheric correction, which is another story. But anyway, you can then go through that process and generate maps of whatever you're interested in. It's just this guy here. The instrument that was making the measurements put out those kind of units, so it's like 4,000, and that's been multiplied by 100,000, so it's still per steradian. So that's really something like 0.004 per steradian, which would be my units. And I think before, my database works in the normal units of like, here's, 0.05 per steradian. So I just take the instrument numbers, divide by 100,000, and then match to my database. Yeah, Lydia.
I would have a question. You said something about the non-uniqueness of the lenses.
Yeah.
If you're taking a pixel by pixel, what are the chances that that pixel next to it will give you the same spectrum?
Yeah.
The places that are the same?
Yeah.
Also, if you take the image from today and then look at the image from tomorrow, would it actually give you the same?
Yeah, okay, good questions. I'll talk about the non-uniqueness a little bit more. And I should also comment, when I retrieve this depth here, that's the depth at the moment the image was taken. So you need to also account for things like tidal water depth going up and down. So when you're finally done, I have to then go find out what was the tides at the time of this image, and then refer the depth to mean sea level and things like that. But yeah, I'll talk about the non-uniqueness business later on here. Okay, here's another area. This is Lee Stocking Island. There's an area here that's what's called Uod sand. There's an area out here that's coral reef. It's called Horseshoe Reef. There's areas past that that are dense seagrass beds. there's areas in here that are mixtures of sediments and corals and turf algae and seagrass and so forth. So anyway, we took this image, which was acquired by a sensor called PHILS, which stands for Portable Hyperspectral Imager for Low Light Spectroscopy. It was a Navy airborne system, hyperspectral system. And so we have pixels here, roughly a meter resolution. So anyway, the Navy flies over, they get the image, they do the atmospheric correction, they then give me the final thing and say, now run your retrieval algorithms and see what you can come up with for bottom depth and bottom type. So, and then they had also sent people out in a small boat that just went back and forth with an acoustic pinger getting bottom depths here. So every little black dot there, they have an acoustic depth, measured from a small boat. And you'll notice it kind of stops where the water gets shallow, so people don't like to drive their boats in 1 meter of coral bottom. Okay, so anyway, we have that we can use to validate the retrievals. And you can see here depths along the shore I've just kind of coded as 0 to 2 meters, and then out here the deepest water is about 12 meters, 11 or 12. And like along here it's sort of 4 to 6 meters. Okay, and then also, I didn't mention it, but right up here there's a really big shark that I ran into snorkeling one day, but that's a different story. I didn't stay around to get any pictures of him, so. But what I was doing was out here snorkeling around to get some visual idea of, what does this bottom actually look like. So I was getting my validation data there. Okay, so we do the retrieval, and here's different ways to look at the results. So we have over 11,000 points in this image where I have an acoustic depth that I can compare to. So here's the spread of values, acoustic depth versus my retrieved depth. Crystal is the name of the software that I developed here. It stands for something like Comprehensive Retrieval of, Comprehensive Retrieval of Image Spectra from a Table Lookup. And then I tacked onto it, what was it? Multi-environmental techniques, MET, multi-environmental techniques based on hydrolite. So crystal meth was my software. But then I thought, well, the Navy's funding this, and given how uptight Admiral Wilson is about being on time to lectures, probably drop the meth part and just call it crystal. So anyway, you can see here's the retrieval. Now, the acoustic depth can be anything. The retrieved depths can only be whatever depth I ran the model at when I created the database. So you can see there's kind of lines here, and then they're a little thicker out here. That's when I was running it like 10 meters, 11 meters, 12 meters, whatever, out to 15. So that's why you get that kind of pattern. Okay, so it's a pretty good fit. There's variance, of course, but on average here of all these points, they're within 3% of the correct value. The mean difference is about 9 centimeters. Standard deviation is about 0.74. And most of the points lie pretty much on close to the 1-to-1 line with these occasional outliers. It just doesn't show up in that kind of plot. Here's another plot of the acoustic bathymetry versus the retrieved bathymetry, and there's this kind of bimodal distribution here. Looks pretty good. And if you look back here, there's a shallow area, so a lot of points that were kind of shallow, and then there's a deep area out here, and there's kind of fewer points that are in between depth. And so that's what you see here. A lot of shallow water, some deeper water. There's a section where there isn't much. It's like 6 or 7 or 8 meters. But you just look at that and say, yeah, that's not half bad for retrievals. Another way to look at the retrievals is I plotted little histograms of the absolute difference in depth of retrieved minus acoustic, and what's the distribution of those bend in like half a meter, a quarter meter thick bends. And here you see, okay, the bend size was 1/2 meter. I got about 85% of the points retrieved were within plus or minus 1 meter of the correct value. Same thing plotted here now as a percent difference, so just retrieved minus acoustic divided by acoustic. And here you see that like 95% of the retrievals are in plus or minus 25% of the correct value. Now the Navy has a requirement for bathymetry that says we don't care how you got it, just guarantee us that it's within 25% of correct. Whether it's acoustic, optical, a guy in a boat with a string, doesn't matter. So they're happy with this retrieval. 95% of the time they're correct. There's also, when you look at these really bad outliers, what happened when the airplane flew over, it has this inertial navigation thing, and it failed that day. So it was hard to match exactly the pixel in the image to exactly the latitude and longitude of the acoustic spot. So if you look at the bottom there, there's a lot of places where there'll be a coral head like this, and maybe this is like 5 meters deep, but this is only 3 meters. So I might have an acoustic ping right here that says it's 3 meters deep, but I'm actually looking at an image pixel that was really here. It was maybe 5 meters away, and it was 5 meters deep. So the retrieval says 5 meters, the acoustic says 3, but it's really a problem of being a few meters off on the matchup there. And that's another story. When I was trying to work on these matchups, and we know like where this point is or this point is, but you don't know these points. So it kind of becomes more inaccurate as you go offshore. And I remember in this image, I kept kind of being like off by a meter or so out there. I couldn't figure it out. Well, the latitude, longitude stuff from the acoustic guys on a GPS was in terms of latitude and longitude. The other image stuff we had, some of it was in terms of what's called UTM, Universal Transverse Mercator Coordinates. And what that comes from is taking a plane, and so here's the Earth, you fit a plane to it, and you get these UTM coordinates, and here's the lat-lon coordinates. And just over the kilometer scale of this, there's a little mismatch that was of order a meter. So it turns out the Earth actually is round, it's not flat. And I was astounded that even just over this like couple of kilometers here, you could see the difference in a flat Earth and a round Earth. And that was throwing things off by 1 pixel. So anyway, that's the kind of stuff you have to deal with. Here's the bottom reflectance map. So here I've plotted from the retrieved bottom reflectance, whichever one it was at each pixel, I just plotted the reflectance at 488 nanometers. Now that's what you would want to know if you were going to fly over this area with a 488 nanometer LiDAR and use it to measure the depth from a bathymetric LiDAR. So you want to know, well, here I'm going to get a really strong return, out here I'm going to get a pretty weak return, so maybe my LiDAR will work well here, but it won't work very well over here because the bottom's just too dark to give me a return. But anyway, you look at this and just visually you say, yeah, this is pretty good. This was that bright sand stuff. There's this coral reef here, and then here was this dark seagrass bed out here. So just qualitatively you can tell it's okay. Now we didn't have pixel by pixel data on what the bottom is here, so I can't show you that kind of plot, but qualitatively it's certainly correct. Here's a thing now that on the retrieval of bottom type, where I've done things a little bit differently. This is reflectance at 1 wavelength, and here I've done a bottom classification thing where it's ooid sand, it's darker sediment, it's dense vegetation, it's kelp, it's infinitely deep, whatever. So what you see here is, okay, yeah, this is sand, I know that's correct. There's this mixture of coral, sediment, algae, whatever, running along there. I know that's correct. Then out here, where it says dense vegetation, that's generally correct, but you see a whole lot of little pixels here that are coming through actually as pure corals. And you think, well, I don't think that's correct. There's a lot of seagrass out there. The corals are back here. You see red pixels here for corals, so those are probably correct, but they're not correct out here. And what that is speckled due to whitecaps. So we didn't try to do anything to remove whitecaps from this image. Well, this is offshore, the waves are coming in this way, so we're getting waves with whitecaps over here. Then when it gets into the shallow water, there's no more whitecaps. So if you trace these down, pull out one of these pixels right here, look at the spectrum, and you look at it and say, yeah, that looks like a bad spectrum. It's way bigger than it should be, and that's probably a whitecap. Okay, more on that in a minute. Now, one of the nice things about matching to database spectra, as opposed to just matching to a model, is in the model, you force it to, find the best fit, you get one answer. Here, I get the one closest fit, but I can also look at the ones that were not quite the closest. So here's just one image, for example. The red curve is the measured image from the fill system. The blue curve here is the closest match from the database, okay? And then the next 29 green curves, or there's 29 green curves, those are the next closest matches. So what I plotted here is the 30 closest matches to the data, to the observed spectrum. And so now, I can say, well, if I'd had like this little bit of noise, and we know the fill system kind of goes bad right at 400 because of instrument calibration. So maybe if the red curve had come across like this, it wouldn't have matched this particular spectrum. It would have been one of the others. Or maybe a little bit different noise out here. It would have caused one of the other spectra to be the closest. So you can say, well, okay, let's look at the closest 30 or 50 or 100 or whatever. And then what's the distribution of retrieved depths for those spectra? So I plotted here the depths retrieved from the closest 30 matchings. And here it is. So for this particular pixel, was somewhere between 10 and 14. There's a bunch of them that matched about 11 meters. There's another little blob that kind of was about 13 meters. So I could just say, I don't know which one of those is really right, but I can pretty well guarantee you this bottom depth is somewhere around 11 or 12 or 13 meters deep, certainly no less than 10, certainly no more than 14. So I get to put some error bars on my retrieval. And at this particular pixel here, the acoustic depth was actually 12.77, so it's right here. And the closest matching spectrum, the blue in here, gave 11.3. If I take the average of the 30 closest, I get 12.3 meters, and the median was once again 12.3. So I can say, whether I use the average, the median, or what, I'm pretty darn close to the acoustic value, and I could say, well, okay, I'll give you an answer of 12.3 meters plus or minus a meter or whatever you want. So I put the standard deviation was 0.9 meters. So that's very useful when you give the user this thing to say, here's my error bars, pretty sure about this depth, not so sure about this other one. So often the estimate of your accuracy is just as important as the answer itself. Okay, here's the same thing for that one pixel there. I looked at the 30 closest bottom matching spectra. Well, here they are. So here's the number, let's see, the closest match is kind of in purple, but it's right under the blue line here. And the next 29 are the green ones. The most frequently matched was this red curve. Now, every spectrum matching has something different about it. It could have the same IOPs and a different bottom reflectance, or the same IOPs and the same bottom reflectance, but a slightly different depth. So somewhere in there will be something different. So this red spectrum here, that bottom type, was actually matched 13 times, or chosen 13 times. And like the ones up here were only chosen once or twice as a possible bottom type. So anyway, I say, okay, here's my 30 closest matching bottoms. What were they? Well, the one that's the closest and the most frequently retrieved bottom was 30% sand and 70% seagrass, because I took those measured spectra for like sand, seagrass, coral, and I also did some mixtures of those. And then the other spectra here, whichever one it is, they're also mixtures of sand and grass, sargassum, turf algae, macrophytes, etc. So I'm pretty confident that whatever was on the bottom here was fairly dense vegetation, probably seagrass. Could have been something that has a spectrum kind of like seagrass. It's hard to optically tell a green seagrass from a green something else, but we're pretty sure what the bottom type is. And then if we look at the IOPs, every single IOP retrieved the same absorption spectrum. Then here's the retrievals of the scattering, and here's the retrieval of the backscattering coefficients. Now, does this make sense? Okay, we're in 12 meters of water, and what really dominates how much light gets down to the bottom, reflects, and makes it back out is the absorption coefficient. So it's really confident that this is the absorption coefficient. A little less confident on this, but it came out okay. The backscatter, it's off by, here's like 0.05 to 0.01 almost. There's like a factor of 2 error or uncertainty in the retrieved backscatter coefficient. Well, does that make sense? Yeah, because here's the surface, here's the bottom, that's about 12 meters. So what's dominating the water leaving radiance is that light that got in, made it down to the bottom, reflected, and made it back out. So depth, the absorption coefficient along the way, the bottom reflectance are the big things. The backscatter coefficient is how much light got in here, got backscattered by the water column, and made it back out. Well, that backscattering is almost negligible compared to the bottom reflectance. So what it's telling you here is I just don't have much idea about the backscatter coefficient. It's just not important enough to really affect the water leaving radiance. So that makes sense. Okay, yeah, I think I've already said that. There was a big comparison study. There's a number of people around the world doing this kind of work. They all have their own algorithms, etc. So there was a big meeting back in, like somewhere around 2010 or so. So we all got together. We picked a couple of images, one from like the Bahamas here, one from Australia, so forth. And the rules of the game were we were given our images, we did our retrievals, and then an independent group from the University of Queensland, all we did was we send them our answers, they compare the answers and see who did well and who didn't. So, and you didn't get a second chance. First time, that's it. Okay, so Zhongping Li has a technique. Here's Crystal, here's somebody else's technique, somebody else's, and then there's an old kind of pencil and paper method. So what's shown here is the processing time or pre-processing. So in my case, it took me 45 hours to create this database, but I only have to do that once, and then I can use the database from there on out, at least for the Bahamas. Then the second number is how long did it take me to process the image, and then the third number is how many pixels per second was my retrieval thing working on. Well, so here's Zhongping Li's algorithm, for example. He doesn't have to do any pre-processing. He's not creating a database. And it took him 45 minutes to process the image, and then it took me 45 hours to create the database, but I can process the image then twice as fast. Here's one, no pre-calculations, but 12 hours to process the image. And then the winner here, no pre-processing, but it took 1,100 hours to process the image. And at this point, they said, maybe we need to look at this code a little closer. Well, they were actually doing their processing is an IDL. And like, this is just basically a big do loop thing. And the worst thing you can use for MATLAB or IDL is a big do loop. That's what Fortran's for. So anyway, the bottom line is we all get pretty much the same answer. You know, Zhongping Li gets an RMS error of 1.12 meters and I get 1.14. You know, that's no difference, you know, 0.86 and so on. So, and you know, these guys get basically the same kind of quality of retrieval. It just took them longer. So anyway, it doesn't really matter which algorithm you use. If you've got, you know, good atmospherically corrected spectra, you'll probably get a pretty good retrieval. Okay. So then there's an instrument called Worldview 2. It's a commercial satellite. It gives you like meter scale pixels, but you just get the image, you're on your own to do the atmospheric correction. NASA's not in the loop on this. So you can go buy a Worldview 2 image of anywhere in the world. And here's one right here. This is from a bay in Florida, and that's kind of a false color thing. The reddish looking stuff is land, and then this is sand and whatever, and there's a little channel here going out into the main part of the bay. So they give me this image. They say, Curt, work your magic on it. So I do the retrievals, and here's, I have some AC9 and some Hydroscat 6 data from one spot in here somewhere, so I could kind of use those to get an idea of what the IOPs are like. I sort of took these AC9 spectra and sort of expanded it. So here's the range of APG, particulate and dissolved, and here's the range of the backscatter coefficient. So I created a database with this grid of IOPs, and these points are the ones where I actually had AC9 measurements and hydroscat measurements. So you can see that any of these measurements somewhere ought to be described by my database of IOPs, and similar sort of thing for the bottom reflectances and the bottom depths. So I create the database, I process the image. Here's two different retrievals from the same image. Now, I said you have to do your own atmospheric correction. So the Navy guys I'm working with, they did the atmospheric correction two different ways. One of them is called empirical line fit. That should be ELF, empirical line fit. And then there's a radiative transfer code called TOFCA, and they did the correction with these two different techniques. And they said, here's the two images, do your retrieval. Well, if you just show me one of these, it looks perfectly plausible. You know, here's the land over here, or some of this is actually dry at low tide and it's wet at high tide. That's emergent vegetation. And so, you know, that's not bad. Here's obviously it got the channel here of deeper water. And these retrievals said, well, this channel must be like 4.5 or 5 meters deep. So, okay, I can believe that. I haven't been there. Looks okay from the figure. But then the other retrieval here, once again, qualitatively it's believable, but it says the channel is more like 2 or 2.5 meters deep, not 4.5 or 5. So which is correct then? I don't know. So we have some acoustic bathymetry here where they ran around in small boats and got bathymetry at all these spots there. And so then I just, along the bathymetry transects here, I just coded it. If it's 0 to a meter deep, it's red. If it's this orange color, it's 1 to 2, yellow is 2 to 3, and white was greater than 3 meters deep. So you can kind of see right here, crossing this channel is somewhere around 2 or maybe a little bit more than 3 meters deep. There's more than 3. And here, this area right across here is kind of 1 to 2 meters. Okay, believable. So now take the acoustic bathymetry, go back and see how well these two retrievals did. The answer is they're both crap. Okay, here's the one here. The acoustic depth, if it's say the acoustic was 2 meters, I'm retrieving like 3.5. So all this blob of points up here. And then once the acoustic gets to be more than 2.5 or so, it kind of levels out and I just keep retrieving 4 meters. So that ain't so good. Here's my little matches here where I'm only getting half of the points within plus or minus 1 meter, but the water's only like 4 meters deep anyway, so that's not very impressive. If I look at the percentage of good retrievals, 9%. Well, that doesn't quite satisfy the Navy's requirement. I take the other image, it's just as bad, you know, for the very shallow water, you know, 1 meter is giving me kind of 1 meter, not too bad. But once I get deeper than about 2 meters, even though the acoustic depth might be 4 or 5, I just keep retrieving 2. So once again, it's a little better on the statistics, but still not overly impressive. Here I'm only 46% of the retrievals meet the Navy's requirement. So that's not so good. So now what's the problem? Well, is it bad RRS spectra? Do I not have a good database or what? So if we look here, here's a couple of, in the, where is it here? Okay, so here's, let me think here. Yeah, so this kind of greenish curve is remote sensing reflectance spectrum as atmospherically corrected using this empirical line fit technique, which we haven't talked in here about. And then the blue curve is the closest matching database spectrum. Well, it does pretty well. Here's another point here in optically deep water where the orange curve is the measured remote sensing reflectance spectrum and the red curve is the closest matching database spectrum. Well, that's not too bad. Here's a couple of spectra from shallow water, which was 0.7 of a meter with a sand bottom, and you can see the measured and the closest matching database spectra right on top of each other. Here's another one now, the same pixel. This is ELF correction, and this is the TOFCA correction. So once again, given that RRS spectrum, the red line done by the atmospheric correction, there's a database spectrum in there that matches it just very, very well. So the problem is not that the database can't match the spectrum. The problem is I have 2 different atmospheric corrections and they're giving me totally different remote sensing reflectance spectra. And so if you have, you know, different atmospheric corrections giving you different answers, you're going to retrieve different, whatever it is you're interested in, chlorophylls, bottom depth, whatever. So it's absolutely mandatory that you have good retrievals. And when we dig into this a little bit more, I was able to show that neither one of your atmospheric retrievals were any good because you didn't have the input about atmospheric conditions and so forth to do that atmospheric correction correctly. So the end result is we were never able to use this imagery because we couldn't do a good atmospheric correction. That's a long story. That's almost like a whole nother lecture on how to do these atmospheric corrections when you're in shallow water. Yeah.
I have a question that's related to what you're describing right now, but so I don't know about rapid eye.
Yeah, I've never used it.
They're optimized for spatial, not spectral.
Yeah.
You're using a totally spectrally method, you're not using any spatial information.
Right. That's another thing that I haven't talked about here, but I have done a lot of work on that where instead of just using 1 pixel at a time, you maybe use like a 3x3 or 5x5 block of pixels and do some kind of averaging, smoothing, whatever, and retrieve that and then move over 1 pixel but still use like a 3x3 block. And so what you can do there, and it works pretty well. Let's say you've got a 3 by 3 block of pixels. And this is the one you're interested in. Well, maybe it has a white cap in it, and the others maybe don't. So what I would do is I would plot all 9 of these spectra here, and so they look like this. And then, oh, here's one that's way up there, and you say, and this is out in the IR. So you say, oh, that's got to be a white cap. It's really bright in the IR. So throw that guy out, and then do the retrieval on these spectra. And so it enables you to, if this one just happens to be a white cap, you can still do a retrieval around here, and you get, it really smooths out the quality of things, and it's a way to get rid of the occasional white cap or whatever happens to be. And of course, you're smoothing things. If you average a 3 by 3 block, now you're in like a 10 meter by 10 meter resolution, not, you know, a 1.5 by 1.5. So there's a trade-off there. But yeah, I've done a lot of stuff like that. It can work fairly well to get rid of these little anomalies here. Okay, so slightly different problem here. The state of California is really interested in mapping their kelp forests. Well, that's like the easiest remote sensing reflectance problem there is, because you have this reddish kelp floating right on the surface of, let's say, blue or green water. So it's no problem to spot kelp. Here's flying a sensor similar to Phil's along the California coast. This is land, this is water, and generating maps of where the kelp is. And it's been classified by the percentage of coverage. 0 is no kelp, up to 100% in the blue here is just solid kelp at the meter scale of the imagery. So if we just look at one of these little areas here, well, here's the kelp map from 2002. They flew again in 2004. So it's considerably different. There was a lot of kelp here in 2002, and the kelp is kind of gone in 2004. Now, what causes that? I don't know. I'm just the radiative transfer guy. But this gets the kelp biologists all excited. And this is why they want to be able to just like fly over once a year, get this imagery, get a kelp map, and then they can say, wow, something's really going on here. We need to go out in the field and do our water chemistry or whatever it is and find out what happened to the kelp. So very useful techniques. You're not ever going to get a map like this from MODIS, for example. You know, like here's our 1 kilometer box right there. Okay, here's another map. This is a bay in California. I think it's Humboldt Bay. Here's beach, here's land, and here's the ocean out here. Here's the surf coming into this sandbar beach. And this bay kind of, you know, it drains and it fills with high and low tide. And they fly the airborne sensor, and lo and behold, they see all of this eelgrass kind of growing at the edges of the little channels here. Nobody had any idea that there was even any eelgrass in the bay, let alone have a map of it. So another nice application of what you can do if you have meter scale resolution for mapping things like this. And this whole scale here, this is like a couple of kilometers by 3 or so, I think it was. Okay, back to Lydia's question about non-uniqueness. The Navy came to me back around 2000 and they said, oh, look, Curt, you know, I think we could do some kind of retrievals here on, you know, shallow water bathymetry and so forth, and would you look into it? And I said, well, it's not going to work, because how are you going to tell the difference in clear water with a green seagrass bottom and deep water with high chlorophyll? They're both green spectra. It's guaranteed this is not going to work, but of course I'll be glad to take your money and prove to you that it doesn't work. Well, it turns out it works just fine. And so, much to my embarrassment, of course, well, here's what's going on. If all you're working with is normalized spectra, you can't tell the difference. So here's 2 spectra here. One of these, the red one, is infinitely deep water chlorophyll of 10, and the other one is 2 meters deep of pretty clear water like the Bahamas with a seagrass bottom. And they're both green spectra that you would have a really hard time looking at those and saying which one was which. But if you have well-calibrated remote sensing reflectance spectra, then there's no mistaking them. The blue spectrum, the deep water guy up here, the red spectrum is the shallow water with the green seagrass bottom. So those are easily distinguished. And what's going on here is in the clear water with the grass bottom, you've got this dark green bottom. You're not getting much reflectance off of it, so you have a low spectrum. In the high chlorophyll water, you've got all of these phytoplankton in the water. They're scattering like crazy and of course absorbing, but you get a lot more scattering from the high chlorophyll water column that makes your spectrum higher. So it turns out it was easy to tell the difference in these two cases, and now I understand why. So far there hasn't been any real uniqueness problems with this technique. Yeah, Mortimer. It's just that I took the maximum value, set it equal to 1. Yeah.
Your explanation is opposite.
Oh, did I? Okay, wait a minute. The blue is the deep water. Hang on. Red is the infinitely deep water. Okay, I guess I said that backwards. I was thinking that the high... Okay, so as you were then. So it must be that the deep water case was getting more reflectance off the bottom, and that was a bigger contribution than the backscattering by the chlorophyll particles in the red. Okay, I was thinking it was the other way around, but yeah, good catch. Yeah.
And I would also, to me, those spectra are tremendously different in shape.
The two on the left?
Yeah, I mean, even normalized, I can tell you that one of them is packaged phytoplankton. I mean, a packaged seagrass with really high pigment and all the peaks are flattened compared to chlorophyll in cells that are small and relatively unpackaged compared to the bottom. So it's funny because we sort of like, oh, there's that percent. I'm like, oh my gosh, it's tremendously different. And inversion would catch that in a second. I get my spectral.
Okay, well that's good to know. See, that just shows you the advantage of hiring an expert instead of a radiative transfer guy to look at spectra.
In the fluorescence,
Yeah,
they're both fluorescing, but you have so much reabsorption in the blue case of the grass bottom. It's reabsorbing all of its own fluorescence. So there's lots of really interesting biology in those normalized spectra.
okay,
So,
that's good to know. Okay,
call the Navy.
all right. Okay, here's another kind of comment on atmospheric correction. So in some of that Lee Stocking Island imagery, the first time the Navy corrected the imagery and sent it to me, I didn't get good retrievals. So here, right here, the blue is a line of acoustic bathymetry kind of cutting across the coral reef from shallow water to deep. And the first time I did the retrieval, it did okay in the shallow water, but then it just leveled out here and it couldn't get any deeper than about 4 or 5 meters. So that clearly wasn't good. So I sent the image back. Well, actually I looked at the spectra, and here's what the spectra looked like. They're all leveling out here to about 0.003 per steradian. And so the reason it can't get a deeper retrieval is the only way you could get this much water leaving radiance or this much reflectance back at 700 or 800 nanometers is if the water's shallow and you're getting reflection off the bottom. So I sent them these kind of plots and I said, look, this is not a good atmospheric retrieval. So redo the atmospheric retrieval, pay a little more attention this time. They reprocessed the image, sent me the new image with spectra that now go to 0 out here, and then the green curve is the retrievals with the good atmospheric correction, and it's doing just fine all the way down to almost 15 meters. So once again, bad atmospheric correction, you're not going to get good results no matter what you do. Okay, here's this, I talked a little bit about glint removal. So you get some spectra here that kind of look believable, and then you look at these spectra here. There's one that's really bright, and then there's a couple, that's this one. There's a couple that are not quite as bright, and then there's the surrounding ones here. Well, you look at the image long enough, you say, yeah, that's a white cap there. So how do we get rid of the white caps? Well, for deep water, people have cooked up all kinds of algorithms where they look out in the infrared, and if it's too big of a value and so forth, they say it's a white cap and they throw it out. If you do that here, you actually do remove most of the white caps, but you also remove the very shallow waters where you're actually seeing the bottom. So we decided we'd rather have good retrievals of the very shallow water and live with not getting good retrievals out here in the deep water wherever there was a white cap. So once again, you just have to balance, would you rather get rid of the white caps out here, or would you rather have good retrievals in the very shallow water? Okay, I'll just finish this up with some comments about data management, which gets to be a real problem with this kind of imagery. So here's my little image of Lee Stocking Island right here that we've been looking at. And then that's a part of this surrounding area here. Here's Lee Stocking Island, these other little islands, nice kayaking there. Anyway, this little one image that I process is from right here. It's from right here, and this image is from right here, and here's all the rest of the Bahamas. So if you talk to the coral reef guys, they say, oh, we'd love to have like 1 meter or 10 meter image, analysis of all the world's coral reefs, and oh, we can do wonderful science with that. Well, just to do the Bahamas area, the ratio of the whole Bahamas Banks area here to my image is something like 200,000 times as many pixels. And yeah, you could go out there and you'll fly your airplane back and forth in a couple of weeks. You'll image that whole area. And then you think, well, I need to do all of the world's coral reefs, which are shown here. I just was looking right here. Well, like all of the world's coral reefs are like 1 million times more than my one little image. And then I'm going to have to make a bigger database, because the one I made here was 250,000 spectra, but that was just for Bahamas IOPs. And if I go to Indonesia or somewhere, those are different water IOPs, maybe different bottom reflectances. And pretty soon I need a database that's maybe 100 or 200 times bigger than the one that's just valid for the Bahamas. And you keep playing around with this. Well, if I get, let's say I'll settle for 10 meter pixel size, well, I'm going to have 1 million times the area. I'm going to have, if I go from 1 meter pixels to 10, well, that cuts things down by a factor of 100. Wavelength's the same, still hyperspectral. The database is maybe a couple 100 times bigger. And I end up with having to do maybe a couple of million times more just image analysis. And what took me an hour on a PC is now going to take 200 years. So the guys in Hollywood, they would think, well, that's no big deal. I mean, that'll be like 5 minutes for us. But for me on a PC, 200 years is probably a little overdoing it. So you kind of have to consider just the magnitude when you get down to this meter scale of what are you going to do with the data. And then that's just the image processing. Then you've got all this imagery stored, and that's not like terabytes. That's like whatever the next one is. There's enormous amounts of data that you don't want to throw away. You spent money to go get it, so you want to archive it. And then all of a sudden you've just got like buildings full of hard drives to store this stuff away. So it's a big issue on just the database management. And after this whole process was sort of up and running, and the Navy now has my Crystal software, and they're out there doing whatever it is they do with it, There was actually a separate company spun off to just do the database management stuff for all of this. Okay, so that's kind of the story there.